Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1967 paper by John Stewart Bell, titled On the Einstein-Podolsky-Rosen Paradox, stands as a pivotal work of 20th century physics, serving as both a clarification of his earlier 1964 theorem and a pedagogical masterpiece. It transformed a long-simmering philosophical dispute about the nature of reality into a concrete, experimentally verifiable question. This essay provides a profound and detailed evaluation of the internal claims, logical architecture, and conceptual framework presented within Bell's 1967 publication. The analysis will proceed sequentially through the paper's core arguments, examining the structure of its reasoning and the precise claims advanced at each stage. The objective is to illuminate the intellectual mechanics of Bell's demonstration, assessing the coherence and force of his argument as it unfolds from its initial framing of the EPR paradox to its final, world-altering conclusion regarding the character of physical reality. This evaluation aims for a deep engagement with the text itself, tracing the unflinching line of logic that Bell so brilliantly constructed. Section 1, recasting the foundational dispute. Bell commences his 1967 treatise, I fundamentally reframing the core issue at stake in the Einstein-Podolsky-Rosen debate. He presents the EPR argument as a demonstration that quantum mechanics, if it is a complete theory, must entail a peculiar non-local connection between spatially separated systems. He then presents the alternative, favoured by Einstein, that quantum mechanics is an incomplete statistical theory, and a more complete specification of the state, through hypothetical hidden variables, would restore a local and intelligible reality. Bell's opening move is to position his own project as an arbiter between these possibilities. His claim is that the question of hidden variables is an entirely legitimate and scientific one, capable of a definitive answer. In these initial paragraphs, he evaluates the prevailing intellectual climate with a characteristic intellectual honesty. He acknowledges the widespread professional sentiment that Niels Bohr's response to EPR had definitively settled the matter, yet he expresses a subtle, scholarly dissatisfaction with the opacity of that resolution. Bell's claim is that Bohr's verbal arguments, while influential, lacked the mathematical precision required to close the case. He implicitly argues that the very possibility of a local hidden variable theory, a description that completes quantum mechanics in a way Einstein would have found palatable, had been dismissed by professional consensus rather than by rigorous proof. His work, therefore, is presented as supplying that missing proof. The initial section of the paper thus functions as a powerful intellectual ground clearing, asserting the legitimacy of the inquiry and framing the central question with a clarity that had been absent for 3 decades. Section 2. The pragmatic simplification to spin correlations. The second major argumentative step in Bell's paper is his deliberate pivot from the original EPR thought experiment involving continuous variables of position and momentum to David Bohm's version using discrete spin variables. Bell evaluates the Bohm-Aharonov formulation, which considers a pair of spin-and-a-half particles originating from a spin-zero state, as a superior vehicle for his analysis. His central claim in this section is that his simplified, discrete system contains the full paradoxical essence of the EPR phenomenon. He argues that the use of spin measurements with Stern-Gerlach magnets offers a more direct and experimentally practical framework for interrogating the core tenets of locality and realism. The explanation he provides is a model of pedagogical clarity. 2 particles fly apart in opposite directions, their total spin remaining 0. A measurement of the spin of one particle along a particular axis immediately determines the spin of the other particle along that same axis, regardless of the distance separating them. Bell evaluates this instantaneous correlation as the central mystery to be explained. His claim is that a local realistic theory would explain this correlation by positing that the outcome of each measurement is predetermined by properties or hidden variables carried by each particle from the moment of their separation. The section's argument is crucial because it makes the problem tractable by moving to a binary system of outcomes, spin up or spin down. He prepares the ground for a simple yet devastating algebraic argument. The internal claim is that nothing essential is lost in this simplification. The philosophical stakes remain identical, while the mathematical and conceptual apparatus becomes immensely clearer. Section 3. The formal definition of local causality. Having established a physical scenario, Bell proceeds to the formal heart of his argument, the mathematical definition of a local hidden variable theory. This section makes the most critical claim of the entire paper, for it is the axiom whose consequences he will explore and ultimately find to be in conflict with quantum theory. He introduces a variable, which he represents with the Greek letter lambda, to stand for the complete specification of the state of the particle pair. This lambda represents the full set of hidden variables or physical properties that, according to the Einsteinian view, would provide a complete description of reality and predetermine the outcomes of any future measurements. Bell then defines the assumptions of his model. The outcome of a measurement at the first station, which he calls A, is a function of the orientation of the local measurement apparatus, designated by the vector A, and the complete state lambda. Likewise, the outcome at the second station, B, is a function of its local apparatus setting, vector B, and the same complete state lambda. The crucial claim, the principle of local causality, is then stated with mathematical precision. The outcome is entirely determined by A and lambda. It is independent of the setting B of the distant apparatus. Symmetrically, the outcome B is entirely determined by B and lambda, with a complete independence from the setting A. This formalizes the intuitive notion that an action performed here cannot instantaneously influence a physical reality far away. Bell's evaluation of this principle is that it is an eminently reasonable, almost self-evident feature of any sane physical theory. His argument is that this assumption of locality is the bedrock of Einstein's entire critique of quantum mechanics. The power of this section resides in its translation of a philosophical intuition into a precise, falsifiable mathematical statement. He also introduces a probability distribution for the hidden variables, rho of lambda, which describes the likelihood of any particular complete state being produced by the source. With these elements in place has constructed a complete, generic framework for any conceivable local realistic. Section 4. The derivation of the limiting inequality, building directly upon the axiomatic foundation of locality. Bell's next section presents the derivation of his famous inequality. The claim of this section is that the assumption of local causality, as he has defined it, imposes a strict mathematical constraint on the statistical correlations observed between the outcomes of the two distant measurements. He begins by defining a quantity, the expectation value of the product of the two outcomes, which he designates P over and B. This quantity is calculated by integrating the product of the two outcome functions, over and lambda and B of B and lambda, over all possible hidden state lambda, weighted by the probability distribution rho of lambda. This expectation value represents the average correlation between the measurements for a given pair of settings A and B. From this point, his derivation is an exercise in elegant and simple algebra. He considers a third possible setting for the second detector, which he calls C. He then constructs an expression for the difference between the correlation for settings A and B and the correlation for settings A and C. He writes this difference as an integral involving the factor over and lambda multiplied by the difference B of B and lambda minus B of C and lambda. Here, he makes a clever algebraic substitution, because the measurement outcomes for spin-and-a-half particles are always either +1 or -1. The square of the outcome function B of B and lambda is always equal to 1. He multiplies the term inside the parenthesis by B of B and lambda, which he is permitted to do since its value is 1. This allows him to algebraically rearrange the expression into a form that bounds its absolute value. The result of this short, impeccably logical sequence of steps is the inequality itself. In its 1967 form, it states that the absolute value of the difference between the expectation value P of and B and the expectation value P of A and C is less than or equal to 1 plus the expectation value P of B and C. This inequality is the central mathematical result of the paper. Bell's claim is that this relationship must hold for any theory whatsoever that respects the principle of local causality he laid out in the previous section. The derivation is completely general, relying on no specific details about the hidden variables beyond the assumption of locality. Section 5. The direct conflict with quantum mechanics. Having derived a necessary consequence of any local realistic theory, Bell's subsequent section is dedicated to demonstrating that quantum mechanics violates this constraint. The central claim here is that the predictions of the established quantum formalism are fundamentally incompatible with the principles Einstein held dear. Bell proceeds to calculate the quantum mechanical prediction for the expectation value P of A and B. For the specific case of the singlet state of 2 spin-and-a-half particles, quantum theory predicts that this correlation is given by the negative of the cosine of the angle between the two detector settings A and B. This is a standard and uncontroversial result from quantum mechanics. Bell now has two distinct predictions for the correlations, one from his general framework of local hidden variables encapsulated in his inequality, and one from the specific formalism of quantum mechanics. The final step is to show their incompatibility. He selects a specific arrangement of the three detector settings A, B, and C. For instance, he can orient at 0 degrees, B at 45 degrees, and C at 90 degrees. He then plugs these angles into both the quantum mechanical formula and his inequality. The quantum calculation yields specific numerical values for the correlations P over and B, P over and C, and P of B and C. When these quantum-derived values are inserted into the inequality derived from local realism, the inequality is shown to be violated. The left-hand side becomes greater than the right-hand side, a mathematical impossibility if the initial assumptions of locality were correct. This direct numerical contradiction is the climax of Bell's argument. His evaluation is stark and unambiguous. Quantum mechanics and local realism cannot both be correct. One of them must be wrong. The paper claims, with the full force of mathematical proof, that the statistical predictions of quantum mechanics are of such a character that they cannot be reproduced by any theoretical mechanism that assigns predetermined properties to particles and forbids faster-than-light causal influences. Section 6. The interpretation of the result and its consequences. In the concluding passages of his 1967 paper, Bell evaluates the profound implications of the conflict he has demonstrated. His primary claim concerns the interpretation of the result. Given that quantum mechanics is an eminently successful theory, consistently verified by experiment, the fault must lie with the assumptions that led to the inequality. Bell identifies the principle of local causality as the crucial, and now highly suspect, axiom. He argues that his theorem forces a choice. The world must be non-local in a way that defies classical intuition. The outcome of a measurement in one location can be dependent on the setting of a remote apparatus in a manner that is unmediated by any known physical signal or force. This is a claim of immense physical and philosophical significance. Bell is careful to delineate what his theorem has shown. It has proven that any deterministic hidden variable theory must be non-local. He also extends the argument to show that even stochastic hidden variable theories, where the variables only determine the probabilities of outcomes, are subject to the same constraint and the same conflict with quantum mechanics. In his analysis, the hope of completing quantum mechanics with a more detailed, local underpinning is shown to be mathematically impossible. He concludes with a reflection on the state of physics, suggesting that the non-local character of the theory is a feature to be reckoned with, a fundamental aspect of reality that physicists have been too quick to dismiss. He subtly criticizes the prevailing orthodoxy for its lack of curiosity about these foundational questions, a theme that echoes the paper's opening. The final claim of the work is that the APR paradox is a real, physical feature of the world, a deep puzzle about the nature of space, time, and causality that can be tested in a laboratory. Conclusion: the enduring significance of John Stuart Bell's 1967 paper on the Einstein-Podolsky-Rosen paradox is rooted in the impeccable integrity of its internal claims and the unassailable logical progression of its argument. Our section-by-session evaluation reveals a work of extraordinary intellectual power and pedagogical grace. Bell begins by clearing away decades of philosophical fog, reframing the debate with mathematical precision. His adoption of the spin-based system provides a perfectly distilled version of the APR puzzle, making the subsequent formal analysis both accessible and rigorous. The paper's core achievement is the formulation of locality as a falsifiable axiom and the derivation of its necessary consequence, the inequality. This act alone transformed the discussion, by then demonstrating the clear violation of this inequality by the predictions of standard quantum mechanics. Bell established an irreconcilable conflict between two fundamental views of the world. His final evaluation correctly identifies locality as the casualty, forcing the scientific community to confront the profoundly non-intuitive, interconnected nature of reality that the quantum formalism had long suggested. The paper's claims are not opinions or interpretations, they are theorems derived from clearly stated premises. It is a masterpiece of physical reasoning that converted a metaphysical question into one of experimental physics, thereby inaugurating a new era of research into the foundations of quantum theory and permanently altering our understanding of the fabric of the cosmos. Its internal logic is a closed and perfect system, leading the reader from a set of eminently reasonable assumptions to a conclusion that shatters our classical worldview.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.